Welcome to 5-Minute Lectures. Today we will be starting our lecture series on multivariate calculus, also known as Calculus 3. Today's lecture is all about motivating vectors. The essence of this class is simple. We take everything we learned in Calculus 1 and 2 and redefine it in 3 dimensions, hence multivariable calculus. Although this sounds easy, what we find is that with the extra dimension, we introduce a lot more complexity. And to deal with this added complexity, we need vectors. When we worked in the world of single variable calculus, our input space was the x-axis, a 1D line. And in this 1D line, we could only move in two directions. If you went to the right, your x increased, and if you went to the left, your x decreased. Now, however, in 3 dimensions, our input space is now the xy plane and not a line. Any point on this plane is a possible input, and there are infinite directions we can go in. Hence, in order to regain a sense of directionality, vectors are required. So what is a vector? A vector is a quantity with both magnitude and direction. We often represent vectors as line segments running from some initial point P to some terminal point Q. The length of the vector is going to represent the magnitude of the vector, so the length of the line segment. The arrow on the vector is going to represent the orientation of the vector. And the angle theta that the vector forms with the horizontal is going to represent the direction of the vector. We often notate vectors with the points they're running from, with the arrow on top to represent that it's a vector. Or we could just use variables such as lowercase letters such as u or v to represent vectors. Now often the start point P will be the origin, and we will write this vector as the coordinates of its endpoints. The pointing brackets here simply differentiate this vector from a regular coordinate pair. Vectors can, however, be positioned not relative to the origin. For instance, here, our vector starts at some point x1, y1 and ends at some point x2, y2. In order to rewrite this vector in standard vector notation relative to the origin, we simply subtract the coordinates of the terminal point to that of the starting point. Lastly, we can find the magnitude and the direction of the vectors. We can see that the vector forms a right triangle with the x length and the y length of the line segment, and the hypotenuse as the length of the line segment. We can then apply the Pythagorean theorem, and you can see that the magnitude of the vector equals the square root of x squared plus y squared. The double bars here represent that we're taking the magnitude of the vector. Lastly, for the direction, we can use our trig identities here. Here you can see that the tangent of theta is equivalent to y over x. Hence, we can then use our inverse trig identities to get that theta equals arctan over y, arctan of y over x. Something to be careful about when finding the direction of a vector is when the vector is not present in the first quadrant. Here we can see that the actual angle we want is the angle in green. However, it won't be as simple as using our trig identities this time. First, we can find this reference angle that's present in the right triangle by taking the arctangent of the absolute value of y over x. We take the absolute value to prevent any issues with the domain of the inverse trig function. Now, we can find theta by simply subtracting the reference angle by 180. So you can see that the green angle in green and the reference angle add up to make 180. So to find the angle in green, we take 180 minus the reference angle. For the third and fourth quadrants, we would do the exact same process, except in the third quadrant, you can see instead of subtracting the reference angle from 180, we would add the reference angle to 180. And in the fourth quadrant, we would subtract the reference angle from 360. And with that, we have come to the end of the lecture. I hope you guys learned something new, and please let me know in the comments what other topics I should cover. Thank you.